you circuit jerks. It's time to jump right back into this. We're going to make an audio amplifier, okay? We're going to base this on a chip that I happen to have lying around. It is here in this little tube. I don't even know what the part number is. Let me get the one that's out. Let me get the one that's out. TDA 7293. I bought this like 5 years ago. It's an ST micro device. Let's check it out. Sorry, I get to see my Twitter. TDA, what was it, 7293? Yep. Yeah, that's in my history. Okie dokie. Oh yeah, sure, I'll open Firefox, why not? Or sorry, Foxit, let's do it. Alright. So, multiple BCD technology, whatever the heck that means. Very high operating range, okay. DMOS power stage, high power output. So this is the part that got me interested. It's about 100 watts. That's a lot. That's a decent speaker. I was thinking, let's see, Fender, small guitar amplifier. How many watts is like a regular guitar amplifier? Right, yeah. Let's grab. I want the little one. Where are the little ones? Where are the little ones? Freaking Boromir over here. Wow, geez. Oh, there we go. Yeah, little guy, Frontman 10G. I wash dishes in cars for a summer, and I want to be in a rock band. Yeah, I remember those days. 10 watts, baby. Ooh, man, 10 watts. I love it. I love it. All right, so maybe we'll turn into a guitar amplifier. Who knows? I got plenty of guitars back there, so. All right, DMOS power stage. All right, whoop-de-doo. 100 watts, muting and standby functions, no switch on-off noise. That's good. I saw that. That was actually a big deal. If I press the buttons to turn this thing off and on, like the mute button or the standby button, I do not want to hear this thing pop because that's going to blow speakers out. Very low noise is what also attracted me to this, and short circuit protection is also good. All right, thermal shutdown is also a nice feature. I pretty much just wanted a reliable audio amplifier, and this guy fit the bill. It can do 4 and 8 ohm output loads, so we're doing pretty good. I got the vertical series, as you can see. All right, let's get into it. Okay, so pretty much the main thing you want to look at when you're just looking into getting a new chip is taking a look at the block diagram or the application circuit. So here's the application circuit here. All right, so we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 9 or 10. Capacitors, 1, 2, 3, 4, 5. Resistors. Of course, you got your speaker, which I'm going to have to dig something out for that. A couple of buttons. I see they want a short out to ground whenever they're not in use. All right, so I got you. So V mute, V standby. All right, cool. All right. I feel like this should actually be like up to power, right? It should be up to VCC or plus VS, right? So yeah, that's a good question. So we've got the signal coming in V mute, right? It's going through the switch. That's how you control whether V mute's on or not. So is that connecting to plus VS? Where is that connecting to? Let me just grab this. We'll take a look at what the input voltage is for V mute. So 5 volt. Okay. So it's not VS, because VS, yeah, VS is like plus 40, minus 40 volts, right? So that's not going to be it. So this is going to be from a regulated supply. So what's not shown here is that you're going to want to have a external 5 volt supply from whatever your supply is, okay? Plus VS looks like it wants to be up to 40 volts. I want to see what the minimum VS number is. So let's go back down to electrical specifications. Take a little look at that. All right. Operating range is minimum of 12 to 50 volts. All right, so there you go. It can be plus or minus. I don't see a reason why I have to have a negative voltage. I'm not sure if there's an advantage there. I'll have to look at the theory of operation to see if that is actually useful. Circuit description. Application suggestion. Blah, 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 blah. Okie dokie. All right, this is not very... It's also a short data sheet. That's kind of helpful too. All right, circuit description. Oh my gosh. All right. Okay. All right. Yeah. All right. I'm designing an audio amplifier here. I don't need to know why I'm doing my job. I don't need a grand narrative. Who wrote this? I don't need a grand narrative as to, oh, these days we like to have things that are very high power and low cost and good performance. Yeah, no squat, man. Come on. Safe operating area. Okay. All right. This actually has content. The task of realizing this linear integrated circuit is conventional bipolar technology is made extremely difficult by the occurrence of second breakdown phenomenon. Don't know what that is. Don't know. It limits the safe operating area. Okay, that's what it does. Knowing what something does is just as good as knowing what it is. Right? As a consequence, the maximum attainable output power, especially in the presence of highly reactive loads. Whoa! Moreover, full exploitation of the SOA, which is safe operating area, translated into a substantial increase in circuit and layout complexity due to the need of sophisticated protection circuits. To overcome these substantial drawbacks, the use of power MOSFET devices, which are immune from secondary breakdown, is highly desirable. Active sentences are also highly desirable, but we do what we can. Just want to make sure I'm actually recording. I've done that before. Output stage. Okay, the main design task in developing a power operational amplifier independently of the technology used is that of realization of the output stage. Okay. The solution shown as a principal schematic of figure 6 represents the DMOS unity gain output. Okay, let me just show me the circuit. Okay, so you got your positive voltage, you got a current source reference here. That is going to the gates of 2 P channels. All right. Yeah, I could simulate this if I wanted to, but I just really don't. Okay, you got your... you got an op amp here that is not in negative feedback mode, so it's going to behave like a comparator. So, VI, the reference voltage here is set between these two. Okay. All right. If I knew more about electronics, I could probably figure out what the heck that's supposed to mean. But what I'm guessing this does is it follows the VI here, so the voltage in on VI. I'm guessing that this, through its scheme, follows VI and draws power through here on VO. But now it has these push-pull transistors to really hammer it through. I can simulate that later if I feel like it. But I mean, that's what an amplifier does, right? It's going to increase the voltage. It's going to increase the power. It's also going to provide a buffer so that the input signal isn't going to have to drive anything itself. It's got a high impedance input on that comparator. Therefore, it'll not sag from the input. It'll drive strong. It'll drive heavy. It'll drive amplified. Provided by compensation. Miller capacitor at the amplifier's output to introduce AC local feedback. All right, that sounds important. Miller capacitor. Don't judge my search history. I don't know what you saw. You didn't see nothing. The Miller effect accounts for the increase of equivalent input capacitance of an inverting voltage amplifier due to amplification of the effect of capacitance between the input and output terminal. The virtually increased input capacitance due to the Miller effect is Cm, so C Miller equals C times 1 plus AV, which is negative AV is the voltage gain of the inverting amplifier. Okay, so it's the gain. All right, so you get this feedback capacitance. The more you amplify it, the more you amplify the capacitive effect of the input as well, it looks like. So that means you're going to have a headwind when you're trying to amplify more. It's going to increase that effect. So exploits the direct connection to the Miller capacitance at the output to introduce local AC feedback path and closing the... Okay, all right. So it's compensating. It's got some feedback in there to make up for the Miller effect. All right, protection. Okay, it goes into a muting state and standby if T junction and these temperatures are 150 and 160 respectively. Okay. I wish you would just give me bullet lists, man. Just give me the bullet lists. I don't want to read a paragraph. Paragraphs are old school. Paragraphs are boomer. Bullet lists are the new thing. Give me the listicle. That's why I like the first page the best. The device is provided with both... I feel like it's the first page, and then give me the spec sheet. And here's a suggested on-off sequence. Okay, so you ramp up your voltage supply. Here's your signal in. Okay, you got your reset voltage, you got your mute voltage. All right, so you're going to want to take it out of standby and then put it on and off mute. So here's off of mute. So mute is active low, it looks like. Because when the mute button is on, it crosses this voltage threshold, then the signal can make it through. And it looks like the signal is amplified, I guess. I guess that's what it's supposed to show. Yeah, that's in the scale is in millivolts here, and then scaling is in volts here. So it implies like 3 orders of magnitude amplification. Implies, not actual. All right, single signal standby mute control circuit. Okay, cool. All right. In case you just want to have them do the same thing. So this one's showing I mean, I'm not going to sit here and like figure out what this is going to do, but it looks like, okay, so standby is going to charge up. It's got a 10 micro and a 20K impedance. Mute has itself 40K. It also has this diode so that when it wants to discharge, so if I let mute standby go low, this is going to discharge faster. So what's going to happen here is this 20K is less than the 40K down here. So standby is going to come on first. It's got half the impedance. Sorry, half the DC impedance. Which is what we're talking about here because it's just an on-off signal. And then you're going to have mute has twice the impedance. It's going to charge slower, but then once it's on discharge, it's going to go through the 401, the 1N4148 diode here, and it's going to actually have half the impedance out. So that way mute is the last on and first off. So that's pretty clever. I don't know if I'm going to do that. I mean, I don't see why not. That seems like a good idea. I've got 4148s just sitting around up there anyway. I like head motion towards the tool chest. You can't see. All right, blah blah blah, blah blah blah. Okay, this is cool. Cool. All right, closed loop gain set to 30 decibels. All right, so what's that note? To closed loop gain has to be 26 decibels. All right, so if that's 30 decibels, every 3 decibels will double it. So it's 2 to the power of 10, which is 1024. So it is in fact a 3, roughly speaking, a 3 orders of magnitude gain on this. So that's pretty cool. I measured my guitar once with my oscilloscope. It was in the millivolt range, so that makes sense. And if you want to drive it at the volt range, right, and you've got 8 ohms. So if you've got, I don't know, let's say, I don't know what the voltage output of this thing would be. Let's just say it's 1 volt, right? So V squared over R is the amount of power. So 1 squared over R, which is 8 ohms for the speaker. It's about 1/8 of a watt. But if the power gets up to 100 watts, right, that's P equals V squared over R. So if R is 8, that means R equals V squared over P. So let's solve for V. What's the voltage that it's actually going to push? This thing is expecting to push out, right? So that's V squared equals RP, right? V squared over R, yeah. So 100 watts, that's the P times R, which is 8. And this square root of this is 28 volts. That looks about right. It's in the range. Okie dokie, bootstrapping. I'm guessing that's needed for driving the output or something. I don't know. I'll have to look that up. Boy. All right. Yep. Okay, there's a master slave pin. I looked at the datasheet earlier. I don't really know what the master slave thing is all about on this. I don't know if they like help each other push so they can like get 200 watts total. All right, high efficiency, operated with a 100 volt supply, 120 volt with no signal applied while delivering. The TDA 7296 is a monolithic MOS power amplifier which can be operated within a 100 volt supply while delivering output currents up to 6.5 amps. So 6.5 times 100. That seems like a lot. This allows the use of the device of very high power amplifier up to 180 watts peak power. Okay, so 100 watts is probably just the average power. This thing can actually probably push harder. I wonder what's limiting that. You know, is that the heat? Is it the heat sinks? You know. Another application suggests as the bridge can. All right. Well, this is like getting into the weeds. All right, let's take a look at this bootstrap thing. For compatibility purpose with previous devices of this family, the bootstrap capacitor can be connected either between the bootstrap pin number 6 and the output pin number 14, or between the bootstrap pin and the bootstrap loader pin. All right, so that's just a compatibility thing. When the bootstrap is connected between pins 6 and 14, the maximum power supply voltage in the presence of an output signal is limited to 100 volts due to the bootstrap capacitor over voltage. Okay, I see. So if you do the 6 and 14 thing, the 6 in the output, then you're limited to 100 volts. But that's plenty fine. I'm not gonna push this thing. Shoot, I'm probably gonna operate this thing at like 12 volts. My power supply goes up to 18, and I've got a 12 volt wall wart over there. It does 2 amps. Okay, the pin follows the output voltage. Okay. All right, so this is accomplished by the. All right, so this tells you how to use it. It tells you what the application is, but it doesn't really tell you what it's for. Okay, now this is a circuit that more was I was expecting. Look at this hot mess. Oh yeah, look at that. Jesus. This would take me a minute to figure out how it works. I'm not gonna lie. That structure right here I'm not familiar with. That kind of looks like the inside of a current source. Well, good thing I'm not doing this. Also, this thing needs 4 voltage supplies. That's rich. I'd like to just give it 1 if possible. PCB layout and component layout. PCB and component layout of figure 8. Jeez, look at that. That's pretty cozy though. That's not a whole lot of stuff. Now this is useless unless they actually give you what the components are. So is there a component list? Okay. Here's the modular application circuit with the master and slave. So what do we got going on here? Buffer driver. So the bootloader and the bootstrap pin are both shorted to each other, so they're sharing that. And the output as well. Okay, so they're probably doing, they're probably pushing and pulling together. Yeah. Okay, so this helps you push forward. Let me read that modular bit a little bit. Okay. The modular application is where several devices operate in parallel. Several. Wow. Okay. The modular application allows very high power to be delivered to very low impedance loads. In this type of application, one device acts as a master, the other is slaves. The slave power stages are driven by the master device and work in parallel together, while the input and gain stages of the slave devices are disabled. Okay. Input and gain. Interesting. The figure below shows the connections required to configure 2 devices to work together. The master chip connections are the same as the normal single ones. The output connections can be connected together without the need of any ballast resistor. Yes, that's pretty incredible. Because if you have just if you have very low, impedance outputs, very strong driving outputs, and they're off by even like a millivolt, they can sink a lot of current from one device into another, and that destroys the 2 amplifiers. You end up having one amplifier that's not quite in lockstep, just pumping current into another one and destroying it. But looks like they have some compensation. The slave signal ground pin must be probably because that bootstrapper pin follows the output. So probably they have a higher impedance on the bootstrap pin, and the output will follow the bootstrap pin. I don't know. So that works as like a buffered stage for syncing things up. The slave standby and mute pins must be connected to the master standby and mute pins. The bootstrap lines must be connected together. Okay. Well, I'm not doing that, so I don't care. Do they have just like a regular application circuit and stuff? Am I missing that? I mean, what is regular, right? Modular application. Nope. There's the forbidden zone. Over on Big Mountain. I don't know if you guys ever played Fallout New Vegas. All right, there's the drawing. Cool. There's the vertically mounted package. There's a horizontally mounted package as well. That you can't really see it here, but it just sort of rests, and the tab probably gets soldered or screwed down to the board. Probably just screwed down to the board with some kind of like silver compound to insist with the heat sinking. All right, so that's it. Yeah, so they probably don't have the normal, like this regular application here because they've already got the block diagram right here. All right, so Let's see if this TDA 7293 is actually there. I think it actually is in KiCad. So let's go ahead and pop in and find out. Let me check on my monitor first. There we go. My cat is complaining like really hard. Hey, Dayla. Please. I think she's sniffing the coffee in the air. It's like, what time is it? It's late. It's late at night, and the place smells like coffee. It's coffee, and then it switches very abruptly from coffee to martinis over here. TDA 7293. Look at that. I saw this before. Okay, yeah, that's right. This thing is... I mean, I would have made it a block, but, you know, whatever, okay. We're going to go ahead and place a speaker. That's going to be in the devices library. It's just a symbol. Doesn't matter. What I'm going to do is I am going to have the speaker just go to a 2-pin soldered connector, which is like my habit. That's what I do. It's my favorite thing. Is like, I don't, is it through hole? Is it leaded? Put it to a two-pin through hole connector. That's it. All right, so I need to Alt-Tab my way to victory here. So let's do this one bit at a time. All right, so this output here, I need a bridge here from 14. I'm going to leave 14 going straight, so I'm not going to do this option, okay? But on the output, it goes to... All right, it does feed back to the input. All right, via 22K. Let's do that. Rus. Ugh. Okay. All right. We're going to make this work. We're going to make this work. All right. So there's my feedback resistor. This is pretty standard op-amp stuff. I love EEV blog, Dave Jones. So if you want to know how an op-amp works, go check out his video on that. He cuts the BS. I don't like that academic crap. I just really want to know how to use the components. And then if that like really tickles my fancy, you know, then I will care about how it works. All right, I don't really care what's... Okay, this is just going... All right, this is just shunting. All right, got it. I don't really care how something works until I know how it's useful. All right, because if I sat around and just cared about stuff that was cool or whatever, I don't think... What do they have here? They have a polar. I'm going to go ahead and stick with these polars and non-polars, because there are impedance differences, and that's probably pretty important. Is there like a CP or something like that? Here it is. Yeah, that's what you want. Okay, cool. Yeah, so I didn't really grow up with contemporary music. I think I grew up listening to the oldies station, like classics and stuff, so I probably know more about the Doobie Brothers than I do about the Jonas Brothers. All right, here's the input here, this little oscillating thing. That's the voltage source. It's going to be your millivolts. That's going to be just hooked to my guitar. So here's in positive. That is definitely, I'm just going to go ahead and make that into a connector right now. Now, do they have, you know, they might have barrel connectors in here. That'd be pretty nice. Like audio jack connectors. Here's audio, but that's not what I want. Yeah, that's not what I want. Get out of here. Get out of here. Audio jack. Okay. Okay. What do we got? What do we got? Audio jack with switch. Audio jack. We got a lot of audio jacks. That's audio plug. Yeah, so the jack is the female, all right? And then the plug is the male. That's pretty easy to remember. I could make it easier for you guys to remember, but it would be bordering on obscene. So... This is... Alright, so this is a 2-pole... Audio jack, 2 poles, mono, ground. Okay, I'm kind of curious actually. So let's see if DigiKey wants to be like super slow on me right now. Which it always is. I don't know what's going on with DigiKey lately, but it's having such a big problem fetching price data for me. It's kind of making me crazy. Connectors. All right, watch this. This is going to be painful. All right. Well, here we go. All right, there's barrel audio connectors, so at least they're pretty straightforward with me right there. Okay, this actually looks like the right place. All right, well, that's loading. Let's go do something useful. I'm going to leave that open. In the meantime, let's go ahead and get the rest of this going. So, all right, so our source has a capacitive. All right. And that is a non-polar. So we are now capacitively coupled with the input. That makes it so any DC offset voltage doesn't get passed through. That's all it does. Let's give myself some room because I need to get a resistor in here, because there's also a resistor to ground, right? Yes. So the input's also going to go to ground. Yeah, let's put that right here. Now notice that I give all these components like an extra pin worth of breathing room, because these things aren't going to behave very well if you have stuff connected directly to the pin, like directly to this little circle here. If you try to move it later, it's going to create weird angles and stuff, but if I try to move it now, look at it, behaves really nicely. It just goes back and forth like a little accordion. All right. I could put values on these, but I tell you what, I'm going to put values on these once I've... For slave function. Oh, I don't want to use the slave function. Okay, so I'm just going to put S ground straight to ground. Got it. Okay. Is what that looks like to me. I'll verify that. All right, so S ground, which is pin 4, signal ground. Now I know that's got all these grounds kind of as the same ground, but any PCB designer worth their salt knows to keep their SIG ground, and then there's S ground. Any PCB designer worth their salt knows to keep power, ground planes separate if possible. So you have your audio ground, you've got your power supply ground, you got your signal ground. I mean, the signal is in the output signal. Okay. So that's standby ground. Okay, these are all going to negative VS. Let's go ahead and make a special net for that here in a second. Okay, so all right, pin 8, pin 1. No, pin 1's going straight to ground. Okay. So it's really just pin 8 and pin 15 are going to VS. All right. Here's our negatives. Yeah, I'm going to go ahead and call it negative VSW. So what I say, pin 8 and pin 15? Yeah. So I'm going to need a differential power supply, which is okay, that's fine. Whoops, wrong one. Power pin, let's go ahead and get us a positive. Is there a positive VSW? That'd be nice. Yes, cool. It's good, stuff is making sense. All right. All right, so things are getting a little bit busy under this chip, as you can see. So what I'm going to do is I'm just going to grab negative VSW. I'm going to take it over here. And I'm going to take positive VSW. Positive VSW I might be able to get done up here, but I feel like symmetry kind of screws that up. What I'm going to do is I'm going to put VSW down there. I'm going to go ahead and put the bypass capacitors, the 100 nano and the polar 1000 farad, the 1 millifarad. Those are going to go right down there. Okay, so I'm going to grab this guy right here, copy him. I'm going to copy him, pop them there. Okay, it's very cool. Let's go ahead and get this guy done. Breaking my own rule here. Let's just bring these guys down. See? You break your rule, and then everybody suffers, especially you. All right, and then we're going to bring ground here. Cool, cool, cool. All right, and that's how you do it. Looks good. All right, what else we got? Okay, we got standby. Needs to be decoupled down to ground. Standby and mute both need to be decoupled. All right. That looked like it was small enough that non-polar caps should be good enough. Let's move the reference designator and part value over here. Okay, how about you? How about you? Let's move you up a little bit. Okay, let's have ground. How about there? That's pretty good symmetry. I like that. Okay. Okay. Oh, I screwed up a little bit. Let's move you down 1 pip. All right. Now that's what I'm talking about. All right, you've been decoupled. Although it has, it says non-polar here. Or sorry, it has polar here. Okay. I wonder why it's doing that. If it's really for impedance sake, or is that just for value sake? I got a feeling with 10 microfarad that it's pretty easy to find 10 microfarads in ceramics, you know. But I don't know when this data sheet was made. 2010, so that was 10 years ago. So maybe stuff was more expensive back then. All right, boot. That is pin 6, right? All right, so pin 6, bootstrap. I just need a capacitor between it and bootloader, which is pin 12. Which I don't see. Am I going crazy? All right, I got... What's going on here? What's happening? What's happening? All right, so there's no pin 12 on this thing. What the heck? There's pin 13, 10, 9, 6. I wonder if they meant for... Yeah, I wonder if they want to do the bootstrap the other way. I mean, I can do it that way. I don't really like to change my design just because the symbol is weird. All right, let's see what's going on in the symbol. Do we have invisible pins? All right, so what I did was I opened up the symbol in the library, so I'm editing it now, and I've got the numbers here. So they just didn't put pin 12 on there. That's really weird. That seems strangely lazy. Whatever. I don't feel like swimming against it. So let's just go ahead and connect bootstrap to out. So pin 6 is going to go capacitively coupled to the out. It's uglying up this diagram pretty good. Okay. All right, so the positive side is facing towards bootstrap. All right, that's good. Let's get you out of the way while I go ahead and move this. Oh, nuts. We're going to do this one piece at a time, just like that Johnny Cash song. That's all right. That is pretty painless. Yeah, it's not bad. Okay, cool. We're doing it. We're doing it. Rock on. Okay, and I don't like four-way junctions, so what we're going to do is we're just going to pop that right there. Yeah, four-way junctions are kind of a no-no. People can't tell if you did it on purpose or not, or if you're actually trying to jump over. So if you're going to join with a central line, you do one joint here and then one joint down here. That way they know you're doing it on purpose. Two separate connections, two separate junction circles. Everyone's happy. All right, so we got pin 7 and 13 need to be are going to VS plus, and they need bypass capacitors. So let's go do that. Let's accommodate that. All right, so V from pin 7, it just needs 100 nano. I'm going to move this yet again. It's yet again in my way. Okay. Not that it really matters between pin 7 versus pin what else, you know. Oh, whoa, whoa, whoa. I already hate this. Yep. Let's fix this. Yeah, being kind of picky is sort of what makes you an engineer. So if you ever complain that an engineer is being kind of picky, get bent, I guess. I don't know what to tell you. That's kind of what we do. Details matter, man. And pretty is pretty. All right, so there we go. I think that's okay. Yeah, I think I can stomach that, I guess. It looks a little funny, but whatever. Okay. All right. So now we need a... All right, so I did my feedback resistor. That's done with R2. Okay. I'm going to need 2 switches here. I need them to be latching. So R5. All right, so from mute, which is pin 9 and pin 10, the standby. I think it's time to use a global label. So which one is this? This is standby, STBY. Cool. It's not the worst thing in the world I've done. I've done far worse. So what these are going to do is they're going to remotely connect anything that we copy these to. So right now, mute, it's not going anywhere because I haven't made another one, but I'm going to go ahead and make a mute right here. All right, and I'm going to make a... I always screw up these switch designations, but I think it's going to be a single pull double throw. Or is it double pull single? No, this is a single throw. Double pull single, it's a DPST switch. Find me a switch. Actually, I can just type in DPST. I was wrong, man. Single pull double throw. There we go. I was right the first time. Okay. No, good enough for me. Okay. I need... Oh, you know what? I got this all wrong, man. Let's go ahead and reflect that. There we go. Because this has got to go down to signal ground. There we go. Here I am screwing everything up. Everything up. All right, and this needs to go to plus 5V. So I'm just going to go ahead and put one in here. Oh, wrong one. Power port. So this is going to be plus 5V. There we go. It feels weird just having a straight up going to the power supply. So let's go ahead and put a resistor in line. At the very least, if we end up changing it, we can change it over to a 0 ohm jumper resistor. But I like having the option of putting some input impedance on that, so I don't fry myself. Okie dokie. All right. Yeah, all right, so we're going to need a 10K between that. So we're just going to grab mute, move that here, copy the resistor, put that there. Okay. Bring you in. All right, that's awesome. Now what we're going to do is I'm just going to grab this. I'm going to duplicate it, duplicate block, bring down another one here. I'm going to change mute to STBY. There it is. Oop, there it is. She good. And I already have the mute and standby capacitors. Yeah, it feels kind of awkward having... Yeah, this feels a little awkward having stuff sort of spread out like that. Let's just put all these circuits here. Let's go ahead and put them in the same place. Cool. Cool. All of it's gone, actually, as far as I'm concerned. Grab standby, grab mute. I'm just going to delete this whole thing. Yeah, just delete it. Delete all of it. Make it all go away. No more. All right. Grab standby here. Grab mute. Pretty flags. Wavering. And there you go. Boom. There goes the dynamite. All right, which ground is the speaker going to? All right, just going to regular old ground. I like it. Yeah, this ground is going to be the true 0 volts because we also have the other thing we have is negative VSW, and we also have positive VSW. I don't think we have any other negative voltages or grounds on here. We really just have the one ground. Okay. All right, so VS and pin 15, and all right, so pin 15 and did we get that? There's 7 and 13. Okay, so we did. We took care of that remotely. Okay. I'm gonna move this up because it's kind of ugly elsewhere. I'm also gonna just copy this. There we go. Symmetry. Nope, no, I don't want to grab that. Symmetry. Oh, come on, man. Give me a break. That looks pretty good right there. I think so. Let's just go ahead and move you over to the side. Lovely. Oh, somehow I staggered it one. I'm just sucking right now at placing this. Looks good enough to me. Perfect. All right, Digikey, did you figure stuff out yet? In stock, normally stocking. I believe I want a mono is good for me. I believe instrument cables are 1/4 inch. Okay, there's a lot remaining. That's awesome. Cool, cool. I don't want free hanging. I want board mounted if possible. So no free hanging. Panel mount might be okay. Panel mount through hole might be really okay. Yeah, all right. All right, let's see what they got for through holes. Oh, all right, single switch. Let's see what we got. Yeah, you're gonna see this on a lot of your guitar amps. Yeah, this is a panel mount. There's nothing through hole about this. I don't know why it's even on. I mean, it's got a solder eyelet. That's not really a through hole. That's what I'm talking about. All right. Okay. Sure. All right, I tell you what. Let's just do through hole right. Let's just do through holes. None of this panel mount crap. I mean, I'm seeing some cheap stuff is looking pretty good. All right, whatever. I'll pick this one. Doesn't matter really. All right, so it's from CUI. No wonder it's cheap. CUI does a good job of keeping their costs down. All right, through hole right angle 2 and 3 conductor models with or without tip switch, thread with nut. Okay. All right, so they got 3 different models here. I would like to have the switch in it. That'd be nice. So here's the tip switch. That's the SJ. So Sierra Johnson 63062 Bravo. That's what we got. Okay, cool. That means my schematic should be okay to go ahead and place that. Not what I wanted. Connectors. I think it was just generics or something. All right. Why does it say audio jack 2? Or is it just like regular audio jack? If I type in the word mono, what do I get? Hopefully not mono. Okay, amplifiers, connector, audio jack too. That's probably what it is actually. Yeah. Okay, this looks like what I want. 2 poles, mono with trigger switch, grounded sleeve, switch. Okay, cool. Does this thing have a grounded sleeve? Kind of looks like it does. Don't know. Okay. I don't think it does. Yeah, so it looks like this guy. All right, that looks good. Cool. So how the heck do I connect that? Well, here's signal. That's an easy one. Okay, how about audio jack with trigger signal application? Give me an application schematic. Let me see what that looks like. That's what that's called, right? Trigger signal? Oh, tip switch. I'm completely wrong. Tip switch. Oh, look. From the horse's mouth, it's CUI. Okie dokie. Okay, okay. Example showing the open contact between permals 2 and 10. All right, so it tells you whether or not you've actually plugged something in. I'm not sure if I'm going to do it. I don't know if I'm going to do anything with that signal yet. So I tell you what, I'm just going to take that out to a test point. I can patch it back in someplace else later. I know it looks a little ugly. I'll fix it. I'll fix it. I'm going to call it tip SW. Okay, and now we are copacetic. I need a little space here, guys. Well, whoops, I took the ground with me. All right, cool. And we're back on Earth. Okay. Feels right to be like down here. Feels right to me. I don't know why. All right, things are slowly but surely getting more tidy and orderly and good. Okay, this looks like a schematic that I might actually want to read and actually understand once I'm done reading it. That's a good sign. Now, did I figure anything else out? What is clip detect? What is clip det? Clip det. What are you? Okay. It does not show it going anywhere. All right, so I'm just gonna test point it out too. Oh, it's not even on here actually. All right, whatever. Okay. So S ground, what is that? It's pin 1, so that's actually standby ground. Okay, and standby ground is just going straight to ground. All right. Done. What else? Got anything else for me? Okay, standby and mute. Those have been taken care of. Very cool. All right. I've got the VS and negative PVW. Yeah, so they just call it negative VS again. It's really negative PVW, but yep. Those are both there. I've got the VS and, oh my gosh, this thing is like way up here. There we go. That's more reasonable. Okay. I've got my bypass capacitors there. Those are all good. I just need to assign values to all these. That'll be really quick and a good way for me to check to make sure this diagram is complete. So let's start with the audio jack in. So the audio jack in as a C1 of 470 nanofarads. So 470 nanofarads. Okay. It then goes to a shunt to ground, 22K. All right. I wonder if I still remember how to do the ohm symbol. Was it 0176? No. 0183? No. 083? 086? I don't know. I'm putting like cards and suits on. I'm not gonna uber nerd and waste everyone's time. Okay. So the bypass capacitors. All right, I'll get those. Actually, it kind of is just the bypass capacitors. Let's do the output now. This needs to be 22 microfarads, so 22 microfarad. You can just use the letter U for the word for micro. You could be a huge fancy lad and use 0177. No, 0178. I think my code might be off. Oh yeah. Okay, never mind. I was trying to be fancy, but I think with the font that's in here, it's the codes I usually use don't work. 0176 is the degree symbol. 0177 is the plus or minus symbol. And these are all alt codes, by the way. So you hold alt and then you type these in with your number pad. And 1000 micro. This guy is going to be 100 nanofarad. There's like 0177 was plus or minus symbol. And yeah, this is 1000 micros again, right? Okay, so it's symmetrical. All right, let's give these guys some space. You are coming over here. You are coming over here. You got to come over here. You got to come over there. Beautiful. All right. But those alt codes depend on which font set you're using, so, you know, there you go. Let's check out that feedback resistor. That is 22K, and I am connected to the output, right? Yeah, okay, so output. Then it jumps over VS, and all right. So let's do 22K here. 22K. All right, and then we're going to go to ground via 680 ohm. And a 22 micro. I think it'd be cheaper and easier to get a ceramic version of that. So we'll see how it goes. All right, I think that's about it. Okay. All right, let's do this. I already did the bypass. Let's do the switch now. So in the switch, I'm just going to put 0 for 0 ohm. Okay, because that's just an optional input impedance. I mean, I already have an input impedance. I'll leave it. I'll let it rock. It's no big deal. 10K, 10K, 10K. Capacitance down is 10 micro. All right, and just like all KiCad designs are all circuit board designs, once you're done assigning all your values, once you're ready to go, this thing is kind of getting clipped a little bit. Let me fix that. And let me align these two. Once you're done doing that, it's time to go to, first you got to save. Then you go to Tools, Annotate Schematic. I like sorting by Y position a little bit better. And there you go, all done. Now everything has been assigned a reference designator. I'm gonna just say audio. There you go, that's easy. The grid really got screwed up there. What the heck? Looks hideous. Absolutely hideous. Okay. I feel pretty good about that. Let's shop for caps really quick. What is the cheapest? Tantalum is not cheap. I think aluminum. Aluminum electrolytic is usually the cheapest capacitor that you can get. Those are the sort of can looking ones. You can kind of tell because they're always exploding inside of consumer devices because they want to go with the cheapest one possible, and that's usually the one with a voltage rating that's just barely enough. So often if you have like a busted piece of appliance, something about the electronics aren't working, chances are you go in there, you open it up, it's the capacitors that are blown, and the capacitors are the cheapest part of it. So you can just replace the capacitors and sometimes get a brand new TV out of a dumpster. EEV blog also does a lot of that. Boy, how that takes a while. All right, we're done. Okay, good. All right, so what I want to find out is if I can get 1,000 microfarad. Now, I doubt I'm going to, but it's going to be pretty interesting to see if I can. You see, it doesn't even go that high, so that's not going to happen. That's got to be electro. That's probably going to have to be aluminum. Now, the other values on here, so 1,000 micro, that's definitely got to be aluminum. 470 nano. Okay, 22 micro, I can go. So 22 micro looks like I should be able to make that non-polar. Same thing with this 10 micro. All right, so let's compare prices with 22 micro first, and then we'll check the 10 micro. So here's 22. This is the aluminum. See, the selection in the ceramics are way worse. All right, I'm going to say that I'm going to order 100 of them. Okay. Did that apply? Oh, wow. All right. So this one's going to be 4.7 cents sorted by price. This one is going to be a lot less. Did that not take? Oh, never mind. Okay. I thought I saw ones that were cheaper. Oh, all right. So this is 5.7 cents versus 4.7. So it's actually cheaper. Okay, so the 22s, I'm just going to make them polar. Can I change the symbol? That'd be amazing if I could just do that. Oh, wow, I can just do that. Oh, sweet. All right, so pro tip. Click on a part if you want to change its symbol. The library reference is right down here. So if I want to go from CP just to C, just take the P off and it's all done. Love it. And I don't even need to check the price on this. I mean, let's be thorough. Let's be thorough. Don't be lazy. You drive yourself crazy. My cats are losing it. Yeah, I turned into a cat person. I didn't intend to. Sometimes cats just happen to you, man. Just go outside and get hit with a cat right beside the head. All right, 10 micro. Come on. Cool. 3.43 cents. Okay. Wow. Ceramic, you're kicking aluminum electrolytics butt right now. Good show. Hey man, y'all are fighting to save me money. That's capitalism. All right, cool. Let's just grab the footprint of that. So the footprint here is going to be 0805, my favorite. Okay, let's go back. Let's go back. Is the 22 also 080? It is. It is also 0805. All right, that makes my life easy. Let's go ahead and just save these part numbers for later. I'm going to grab this 0805 from capacitor SMD. Look at all these electrolytic ones. These are surface mount. Yeah, those are surface mount electrolytics. All right, 0805. Let's do the hand solder ones because I'm soft. All right, boom. Oh, I love it. In there, get in there. Oh, I'm just clicking like crazy. I'm like a StarCraft player. I'm an idiot. I'm gonna go 805 across the board. It's gonna make my life easier. Actually, you know what? Let's do 0603s for these smaller ones. I think I already have 0603s just hanging around my house anyway. This thing's being difficult. Okay. All right. All right, let's see if we can find a footprint for this audio connector. I actually didn't check before I did it, so I'm gonna have to make a footprint for that. If that happens, I'm gonna do that off camera, or make a separate video because that can get really tedious. New product. Okay, so there's a pretty small chance that this actually has a footprint. Audio jack 6.5 millimeters horizontal SJ63062B. Yeah, that's probably gonna be a no-go. Oh my gosh. These Nutrix are all over the place. All right, let's see if this thing has a suggested... Where's the datasheet? Did I close it? Let's see if this thing has a suggested footprint. It should. Okay, so there we go. All right. So we've got 7 and... Oh, man, they picked a single reference point. I hate that. Oh, all right, so it looks like it's 5 millimeters between the rows. Wait, and it's not going to tell me how... It's not going to tell me the vertical distance right here? What the heck? Am I just going to have to guess that that's 2.5? I mean, it's not explicit. That kind of sucks. All right, so these are probably not going to fit the bill at all. Good Lord. Boy, these Nutric guys have a lot of connectors in this library. It's almost like the Nutric company actually flooded this thing with footprints. All right, I'll make a footprint for that. I'll do that on my own time. The speaker is getting the easy treatment. It is just getting a 2-pin. There you go. Too easy. Okay. Just checking my... All right, there we go. All right, what else we got? Okay. I have not done these resistors yet. Let's do it. These resistors are pretty specific, so I probably don't have them in stock. So that means I'm going to just give them 0805s. I don't know the alphabet. There we go. Sure. Boom. Okay. And you get an 0805 footprint, and you get an 0805 footprint. You get an 0805 footprint. Everybody gets an 0805 footprint. Boom. There we go. Done. I say boom a lot. I don't know what's up with that. All right, switch single pull, double throw. Wrong one. Let's see. I am inclined to not reinvent the wheel, so if there's a footprint for a single pole double throw switch that's in here, I'm just going to use it because the difference will probably be pennies. It's not worth it. Switch, 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 switch. None. Button. You guys did this to me last time. These are all single pull, single throws. I want a, what was it? Single pull, double throw. Single pull, double throw. All right, yeah. I'd rather have a momentary push. I'd rather have a locked on push button, right? That's what I would prefer. They really don't have those though. Man, what the heck? Oh, you know what? This looks generic. Okay. So I can find that. All right. So let's go shopping. All right, Digikey and your slow butt. Oh, first let me go ahead and find a aluminum electrolytic 1000 microfarad capacitor. Did I already look that up? No. Okay. Let's go ahead and grab that. The voltage rating is going to need to be pretty big. Let's give it at least 100. But really, I'd like to go at like 160 if possible. Yeah, let's... What the heck? Okay. I got a little bit baffled by that. Stubbies. We got some stubbies here. Look at that. I want something small if possible, but alright, what's cheap? What's cheap? What's cheap? $2. Holy crap. Yeah, I mean, it is 1000 microfarads. Man, I think it takes some ripple current. Holy crap. Yeah, you pop these, you're going to know it. Alright, which one's thin? 1.6, 1.6, 1.6, 1.0, alright. That's height. Whoops. Alright, so we've got 0.86, 0.86. God, these are huge. It is what it is. Alright, I don't see a huge disadvantage. Never heard of Rubicon. United Chemicon? Nichicon. Cornell Dubilier Electronics. Nichicon, Rubicon. Okay. My life is in your hands, Rubicon. This is a fat guy. This is a fat boy. Alright, we got 10 millimeter lead spacing. We got 22 millimeter diameter. So let's go find you. Let's go find you something. That's a fat cap, man. That's a fat cap. Alright, capacitor through hole. I don't know if they're going to have that. Oh, these are late. This is a axial package. You don't see that very often. Alright. Alright, so this is diameter D22. Alright, we got some. Okay. Then we got P for pitch. All right. Now this is not a 3-pin snap in. This is a all right. So pitch of 10 millimeters. Okay. Okay. I think this is our guy actually. Is that what this is? A snap in? Radio can snap in. I'll be damned. Here I go cursing again. Boom. Okay. So I think the only thing that doesn't have a footprint right now, like this, I'm pretty sure this library, yeah, this thing comes with a footprint. The only thing that doesn't have a footprint right now is this audio jack, which I got to design one, and these switches, which I gotta go find one. So let's go find one, and then we'll call it a day. Take me to your switches. I need a push button switch. I'm pretty sure. Yeah. Rotary switches. Slide switches, snap action, limited, tactile switches, thumb wheel switches, toggle switches. It might be under toggle switches, but I don't think so. Yeah, this is what toggle switches look like. They look like these big things. Well, it's not popping up because the page is loading. It takes forever on DigiKey for some reason these days. Yeah, these are more what I'm looking at. These are more what I'm talking about. Okay. It's just as soon as this thing decides it wants to load the friggin' web page. Thank you. I have to get back to work now. All right, let's do surface mount. Let's do all these surface mounts. What I'm hoping to do is just have a free hanging circuit board. I'm not going to put this in a box necessarily. Maybe in the next revision I'll do that, but yeah, not now. I also want an off-on. I don't want a momentary. On-off, I'll take that too. I don't care. Oh, wait, do I want that? One, two, three. Okay. I don't know. I think it depends on what the pinout is. Well, all right. Let me see what my... Fine, I'll check the through-hole ones as well. I want an off-on... I want an on-off. Oh, I better specify the single pole double throw. If I can do that. Oh, there it is, circuit. Okay. Oh. There it is. Single pole, double throw. Okay. All right. Let's see what we got. Let's say I'm buying 100 of them. Yeah, it looks about right. It looks about what I was expecting. These things look like they came out of the 80s. I'm into it. E-switch. It's like 67 cents. I mean, I'll take it. Single pull, double throw, on. I don't want on mom, okay? On momentary. I don't want either of these to be momentary. This needs to be like on. Check the data sheet. And I could buy caps. You can put a cap on top of that. Not a capacitor, but like an actual cap like you put on your head. But instead of putting it on your head, you'd put it on the end of this plunger here. Okie dokie. Yep. So there's a schematic symbol right here. So it's either you're going to take this little piece at the bottom here and it's going to slide between 1 and 2 or 2 and 3. So 2 is the common, and that's what we see here. Very cool. I want to know which one's depressed or not, right? I want to know what the default position is because I want to make sure the default position, the out, means that it's not muted and it's not on standby, right? Like, they're active high, right? So let me check that out. Let me check that startup diagram again because I'm pretty sure these are active low signals. Wherever that diagram went. There it is. So there's mute and standby. Okay, so Oh no, they're active. Okay, yeah. So I want when this thing is in operation, I want it connected to plus 5 volts. Okay. Okay, so I want it between 1 and 2. So 1 and 2 when it's plunged in. Okay. 1 and 2 when it's... Oh, wait, is that right? All right, so when you're working on a guitar amplifier, you want to push in to take it off of standby, right? So standby over here, I feel like that needs to get... flipped. Yeah. Because when I push in standby, I want the thing to turn on. And when I push in mute, I want the thing to go to ground. All right. That kind of makes sense in my own head. We'll see if it makes sense anywhere else. All right, latching functions, very cool, very cool. It's got a good cycle life, I guess. Where did it say that? 10,000 typical cycles. That's about what you're going to get for this price. The part number I'm going for is the LC1258. That's this guy right here. I'd really like to know what the heck the... Yeah, this is probably going to need its own footprint made. I think what it's telling me here is that it's by default it's between position 2 and 3 when it's out. That's what I'm getting here. I wish it would tell me explicitly, but this might be a thing where I have to go and learn it the hard way or something, right? But it looks like it's between position 2 and 3 when it's out. All right, so if the mute is out, I'm going to be positioned between position 2 and 3. Okay, by default. That means mute's going to ground, which means by default I'm muted, which is I don't think what I want. When this is out, I want the mute to go to power. Okay. Between 2 and 3 is default. Now, 2 and 3 is default for standby as well, right? So standby. I want default to be off. I want standby to go to ground when I'm not using it. Okay. So I accidentally did the wrong one. So so standby when it's out, it's going to go to ground, which means it's going to be off. Okay, cool. Got it. Mute, I'm probably just going to always leave clicked out. So, because I don't use mute buttons. Really? I don't know. Cool. All right, so I got to do. I got to build a... I need to design 2 footprints. I'll do that on my own time. I might film it and just toss it up in case you guys want to see me make more footprints, but there's nothing really sexy or fun about me doing that. It's me just reading these drawings and like scratching my head a lot and just sitting around with my mouth open. Okay. All right. This is LC1258. LC1258. Is there any difference between these guys? No, okay. It's just the mounting. It's a little different. This has got a back foot. That does not have a back foot. Okay. LC1258. Now, if I'm really lucky, there's actually a footprint for that, but I doubt it. Yeah, I don't think there's going to be anything in here. Yeah, look, there's hardly anything in here. All right, cool. All right, well, that was fun. Hope you guys enjoyed hanging out with me while I design yet another circuit board. The faster I get these churned out, the faster I get the boards ordered, which means the faster that you get to watch me fire them up and test them. These are sort of just fun you know, ways for me to put all this stuff in the video. If you guys want to use it as reference, feel free. But an hour and 20 minutes of me just making a schematic, well, starting to look a little bit like work, but I actually do this for fun, obviously. Hope you guys enjoyed it. Have a good night. It's late over here.